In this video, we're going to talk about finding volumes for the first time. So now we're going to be in 3 dimensions instead of 2 dimensions. We know how to find a flat area using an integral. So we do the integral of the top function minus the bottom function. If that's a flat surface, I could even like draw an area like that here. But what if I want to find the area volume of a 3-dimensional shape? Can we still use calculus to find something in 3 dimensions, even though we only have x and y? And here's what's going to help us. What is the volume of a box? So imagine I have this box. It's kind of long. Like that. So this is our box. What's the area? Well, we find the area of this rectangle on the front. That's base times height or something. So I keep saying area. Volume is base times height. And then we multiply that by the 3rd dimension, which is the length. All right, so what I kind of want you to see is that we have the area of just this rectangle. It kind of looks like a square, but let's just imagine it's a rectangle. I would take that and multiply it by the length. What's the volume of a cylinder? All right, a cylinder has a circle on the end. And then we elongate it. And what is its volume? Its volume is you take the area of the circle at the front, just pi r squared, and you multiply that by the length of the box. So pretty much both of these shapes, and pretty much any shape that's a nice uniform shape throughout, you take the area of one of the sides and just multiply that by how long it is. All right, so it's just the area of the circle at the end, and you multiply by how long it is. All right, so we're going to use that as to our advantage to figure out these more complicated shapes that we're going to find the volume of. All right, so basically we take a circle for a cylinder, we take another circle, which is adding up a bunch of circles to make the full cylinder. All right, well, in calculus, we have a symbol for adding up a bunch of very tiny things. When we first did this, we were doing these Riemann sums. I defined area, and we started making the rectangle smaller and thinner, and it turned into this integral sign. As this integral sign technically represents adding up a bunch of very tiny things, and now instead of thinking about these rectangles being added up, we're thinking about some different shape being added up. So here's a type of problem you'll see in calculus. We can have this solid whose base is the region bounded by this, whose cross-section is a square. All right, so this is actually a circle. The top half of a circle like this. All right, so that's kind of the bottom of my shape, and then each section coming off of it is going to be a square. All right, I'm terrible at drawing these things, so maybe we'll have to look at like an animation in class to kind of see what this might actually look like. But it's kind of this like half moon shape that has some height to it or something like that. This is making it worse. But that's the basic idea. All right, so when we think about this in terms of the calculus stuff and what we saw with the shapes, we want to take the area of one of the cross-sections. So the cross-sections are going to be the area of a square, which is just the side of the square, which is this height here. Square. So the area of a square is just that. And then, like we saw, we just add up all the squares as we go along. Well, adding up all the squares is doing the integral with respect to x. And we see the stopping and starting point. All right, the circle has radius 2, so it goes from -2 to 2. And then we could take the antiderivatives and evaluate it from -2 to 2. All right, again, we're not going to plug in values. Plug in 2, plug in -2, subtract the 2 answers, and you get your volume. All right, but you can see the side of the square is the equation that's given to us. To find the area of a square, you just multiply the side by itself, you square it, and then to find a volume, you add up all those squares together, which is the integral. All right, so just like you're finding the volume of a thing, all right, it's just in the calculus terms. Solid whose base is a region bounded and where each cross-section is a semicircle. All right, so this one, I don't even know why I'm going to try to bother drawing this, but we have the same situation. We have this half circle, but instead of taking a square, each cross-section here is going to be a semicircle. All right, so it's kind of this curve with like a hump on the top because all these are semicircles going along. So we know we gotta find the area of one of these semicircles. All right, the area of a semicircle is pi r squared. But then you have to divide it by 2 because it's a semicircle, not a whole circle. All right, so my area is pi. My radius of my circle is the square root of 4 minus x squared over 2. All right, that's the radius of my semicircle. All right, why is it over 2? Because this is the diameter going from top to bottom. It's only half of that, over 2. All right, so this is the area of each semicircle. And then I need to add up all the semicircles from -2 to 2. I can do a little bit of simplifying. And that is the integral we try to evaluate. All right, if I was doing this integral, I'd pull the pi over 8 out because that's just a constant multiple. And then I would do antiderivatives. And you would plug in 2, subtract when you plug in -2, and find your final answer. Right, so here's one for you to try on your own. All right, same idea. We have a region that's bounded. All right, each section is a square. All right, so it's just like the first example. You figure out what the side of your square is, square it, and then take your integral. All right, so go ahead and try that, and I'll show you the answer in 3, 2, 1. And you should get something like this. So if you look at the picture, this is just a line going down to the right. It creates this kind of triangle. Each one of these cross sections is going to be a square. And so to find the area of a square, it's just the side squared. The side is just the height of this triangle, which is our equation. So that's the area of the square. And then we add up all the squares together. It starts at 0, ends here, which is when the y value is 0. So if y is 0, you can solve x is 3. And this would be the integral you'd have to evaluate. All right, so to find the volume of an object with similar cross sections, you use an integral. You're adding up all of this common shape. And you integrate the usual area formula for that shape. So we've seen 2 square ones. It's just whatever like the equation is squared. We saw a semicircle one, a little bit more complicated. There might be ones that are like right triangles and things, but whatever the basic area formula is, that's what's going to be inside your integral. And you just integrate all those shapes together.